Hello everyone, my name is Marco and today I'm going to talk about sequence-to-sequence multitask learning on semantic parsing datasets. This work has been carried out at Amazon Alexa in Cambridge with Emilio Monti. Semantic parsing is a popular task where we convert a natural language text into meaning representation. However, there is a lack for a single standard for meaning representation. Different datasets come with different meaning representation languages and formalisms. In this work, we use multitask learning to attempt to unify different datasets and train a single model that can be used to parse sentences into multiple meaning representation languages. We focus on question answering datasets such as GEOQUERY and maps, stops, and overnight, but we also consider the impact of a broad coverage dataset that does not only include questions such as AMR. We show here the two main architectures for multitask learning that we use in this work. The top is 1 to n, where we encode with a shared encoder, but we have separate decoders for each representation. At the bottom is the 1-to-1 architecture, where the whole network is shared. The decoder needs to know which representation to parse into, clearly, so we pass this information as the first input token in the sentence, as done in previous work for neural machine translation. Here we show the exact match parsing accuracy for these architectures when training a multitask learning model for all these datasets. So first, let me say that the baseline sequence, so which is the single task sequence models, do not match the performance of previous state-of-the-art performance, and this is not surprising. Our baseline is a general architecture applied indiscriminately to all different datasets, whereas the state-of-the-art is usually some very specific architecture for each dataset. We now look at 1-to-n and 1-to-1 that are highlighted here, and we see that 1-to-1 performs much better, even for MR, which is surprising, being that MR is considerably different from the other datasets, so you might expect it to be better when he has a separate decoder, but it doesn't seem to be the case in our experience. If now we look at 1-to-1 versus the baseline, a single task baseline, we see that the 1-to-1 gets better on parm results. What's not shown here is that the gain in total number of parameters. So for the baseline model, we need to train 5 models, one for each dataset. Whereas for the multitask learning, it's only one model with the same number of parameters. So we pretty much save 5 times the number of parameters. We next look at a critical choice for multitask learning models, which is to auto-sample batches between the several datasets that we want to train from. In previous work, sampling methods have almost exclusively been based on proportional strategies, based on the assumption that the smaller dataset should be sampled from with a smaller probability, so that we don't overfit them. This hypothesis has not really been empirically tested on this problem. So what we do here is that we test that hypothesis by introducing some additional methods and comparing against them. So inverse does the exact opposite as the proportional approach, and is used here to directly verify the proportional hypothesis. So the motivation, if you want, is that perhaps some small data sets are actually underfitting, not overfitting, using proportional. And so if that's the case, inverse might actually help. And then we also introduce the loss strategy, which is completely independent of the dataset size, unlike all the rest, and instead tries to sample from tasks that are performing worse on the development set. Here we show the results for all these sampling methods, and we see that the loss actually performs really well. If we then compare proportional directly with inverse, we see that proportional is not clearly better than its opposite strategy, and sometimes inverse actually works much better. For instance, in the case of NLM maps. So these indicate that that using proportional as the de facto standard for pretty much any multi-task learning setup is probably not the best choice, and might result in underperforming. We next looked at generalization, which is often considered a big advantage of multi-task learning models. And indeed, what we see here is that, so this is a plot for NLM maps, it plots accuracy over a number of epochs, and we see that the gap between the training and test split for a multi-task learning model is smaller than for the single task baseline, which indicates less overfitting in multi-task learning models. And we also know that we actually stop training for the baseline earlier, and this is due to early stopping, which detects overfitting earlier for the baselines and stops them. We also look at the different type of generalization, which is compositional generalization, by benchmarking on a dataset called CFQ. So CFQ has two test sets: a random test set that is sampled randomly as in other datasets. But it also has one MCD test set, which include test examples that contain unseen composition of primitive elements. So we'll see compositions of elements that were not seen previously in the training data. The results indicate that multi-task learning does better at both test splits compared to the single task baseline, and importantly does better at MCD than the previous work, while it doesn't do better at random. And this all suggests that multi-task learning improves and helps with compositional generalization. Finally, we look at auxiliary tasks. So what we do here is that instead of training a single multi-task learning model on 5 models, we train models on pairs of datasets to see which kind of dataset can be helpful to others. So really there is no one auxiliary task that is good for all purposes, but we found some surprising observations. So for instance, AMR seems to be a good auxiliary task, and this may be a bit surprising given that we know that AMR is the only non-QA dataset, so it's a bit out of the domain compared to the others, and it's also the only one that is not graph structured instead of tree structured. However, AMR seems to be useful to other tasks, and this is probably due to its larger scope and its also larger size. Also surprising is the fact that it's useful even more in the one-to-one setup, where it doesn't have a dedicated decoder. And also surprising is the fact that GEOQUERY, which is the smallest dataset, is shown to be helpful for the larger top dataset. So in this work, we used multi-task learning sequence to build a single parser for multiple semantic representation. These models, besides reaching or outperforming the single task baselines, also use the data parameter count and improve generalization. There is no recipe for choosing sampling strategies and auxiliary tasks, and instead these should be treated as hyperparameters to be tuned. Specifically regarding sampling, using proportional sampling or similar as the default choice might not be the best one, and instead different strategies should be attempted. Thanks for listening.